I must apologize. My screen recording software quit unexpectedly on me. But as I was saying, you could see the wave lines, the wave crests, running along here. So the waves traveling in this direction. And here, where the wave crests are in shallower water, they are traveling slower than the parts of the wave that are out here in deeper water. And that causes the wave line to bend. Or refract. So if the waves traveling in this direction here, over here, the waves are actually traveling in this direction. While further out to sea, waves out here are still traveling in that direction. So that's refraction around that point. Now this refraction, as we'll talk about, it's important when we talk about beach erosion. So wave refraction actually helps shape beach erosion. So waves don't only occur at the surface of the ocean. So waves occur anytime there's an interface between two fluids that have significantly different density. So obviously the ocean has a different density in the atmosphere. So waves often form at the boundary between the ocean and the atmosphere. But at the base of the pycnocline, you have the less dense, shallow water above the denser, deeper water. And that density contrast allows for sometimes for waves to form at the base of the pycnocline. That's called an internal wave. And these are hard to sense or to measure, but they do occur in the ocean, these internal waves. A storm surge is a type of wave. It only has a crest, and a storm surge is a bulge of water that's driven onshore by a tropical cyclone or hurricane, or also by a frontal cyclone. Low atmospheric pressure underneath the storm sucks water up and creates a dome of water as well, as long as the wind's piling water up in front of the storm. Storm surges are short-lived, but they can be as high as 7.5 meters. And storm surges, as I said, they only consist of a crest and a trough. And so here is the storm, and here is the storm surge. Seiches are standing waves because they don't travel. They exist in the basin, and it's basically water sloshing back and forth like in a bathtub or in a wash basin. So water rocks back and forth at a specific resonant frequency in a confined basin. That's a Seiche. And there's parts of the Seiche known as a node where the water doesn't rise or fall, that the water height remains stationary. And so here is an illustration of a Seiche. Here's a basin, and the water rocks this way, and the water rocks back this way. And so when this rises over here, the water falls over here. Whenever the water sloshes back, the water rises over here and falls over there. So right here is the node. So if you were on a boat right there, you wouldn't sense any up or down motion. If you're over here, you'd go up and then come down, go up and come down. And here's an example of a Seiche recorded in Lake Erie. So if you're unfamiliar with Lake Erie, it's positioned kind of like this, with Buffalo, New York being up here, and Toledo, Ohio being down here. Now this Seiche was created by atmospheric disturbance, and the blue line represents the water height in Buffalo, New York, where the red or orange line represents the water height in Toledo. So you can see they begin to oscillate where the water height increases in Buffalo, so water height increases over here, but decreases over there. So the water is rushing to this side. And then it flips, the water lowers over here and rises over here as the water rushes back to the other side. And then a large amount of water rushes over to Buffalo, New York, and the water level falls drastically in Toledo. So the water level rises in Buffalo, at the same time it falls in Toledo, and it sloshes back and forth, back and forth. So this is caused by like a storm in November. You can see the Seiche, this rocking back and forth of water in Lake Erie. So a tsunami, which is the same thing as a seismic sea wave, are these very long wavelength, shallow water waves that travel through the ocean. They're caused by a rapid displacement of a large volume of ocean water. Tsunami generated by vertical motion of the sea floor along a fault are technically known as seismic sea waves, but generally and colloquially referred to as tsunamis. What else can generate tsunami? Landslides, icebergs falling from glaciers, volcanic eruptions can generate tsunami, asteroid impacts can generate tsunami, and other direct displacements of the water surface can generate tsunami. Here's an example of an earthquake, how an earthquake generates tsunami. So this is illustration of how the 2011 Japanese tsunami occurred. So you had a subduction zone in which the Pacific plate was subducting under the Eurasian plate. And the Eurasian plate was being flexed down by the subducting Pacific plate. And they were locked together by friction. But eventually this plate snapped back to its original position, slid up, which pushed this large amount of water up over top of it, which created the tsunami, which then propagated away from the earthquake. That tsunami traveled through the Pacific Ocean. And so this is a YouTube video that animates this process, and I'll post this YouTube video on the lesson site. And so since tsunami have such long wavelengths, there is no part of the ocean whose depth is greater than half of the wavelength, so tsunamis are always shallow water waves. So because they're shallow water waves, their wave speed can be calculated using this formula, where celerity equals the square root of acceleration to gravity times the depth of water. Acceleration to gravity is a constant, it's 9.8 meters per second squared. And the depth, d is the depth, and the depth of a typical Pacific abyssal plain is about 4,600 meters. And so using those two numbers, that gives us an average celerity, or average speed of a tsunami in the Pacific Ocean of 671 meters per second, or 1,500 miles per hour in the open ocean. And so these tsunamis travel very quickly through the deep open ocean, so it offers very little time for warning. This is actually the tsunami travel times for the 2011 Japan tsunami. So these white lines right here represent the front of the tsunami at every 3-hour intervals. So at 3 hours after the earthquake, the front of the tsunami was here, 6 hours, 9 hours, 12 hours, 15. You can see the tsunami actually reached the opposite side of the Pacific Basin in less than 1 day. So that tsunami traveled very quickly because they're deep water waves. The deeper the water, the faster the wave travels. And this is variations in the wave height of the tsunami. So where the water is shallower, the wave height increases, and the wavelength decreases. And so you can see these strips of kind of red, where it's this higher wave height. It's kind of, you somewhat map the bathymetry of the sea floor using the wave height of the tsunami at different locations. And that's it for waves. Thank you very much.